and steel are versatile materials. There's hardly a part of our lives where these materials are not present. In nature, iron exists with oxygen in compounds as iron ore. To extract pure iron from iron ore, the oxygen has to be removed. In this process called reduction, carbon is used as a reducing agent to remove the oxygen. The carbon comes from black coal. The coal needs to be preheated in an energy-intensive process before it can be used in iron production. The coal is transported through more than 100 vertical chambers in a coking plant by a sloping conveyor belt. Behind these small oven doors, the destructive distillation of coal takes place. This process is called pyrolysis. The volatiles, town's gas and tar are driven off and carbon remains. After 25 hours, the oven doors are opened. Red-hot carbon emerges as coke. A ram pushes the coke, almost 50 tons, out of the chamber. In this coking plant, more than 5,000 tons of coke are produced every day. In air, the hot coke burns, so it has to be extinguished. In the past, water was used, but valuable energy escaped in the form of steam. In modern operations, the gas nitrogen is used to cool down the coke. The burning coke is then transported in special containers to the dry cooling facility. Here, the inert gas nitrogen is displacing the air and cooling down the coke. Nowadays, the heat of the coke is generating electrical energy and not wasted. The product of this process is a blackish-gray coke with a metallic luster. Made up of 92% carbon, it's ready to be used for smelting. Iron ore is extracted in large quantities from open-cut mines in Australia, Brazil, Canada, Sweden, and other countries. It's then shipped to its final destination. The basic materials for the manufacture of pig iron are transported mainly by ship and rail. They include enriched iron ore, coke from black coal, limestone, which is used as flux and an extra source of carbon monoxide. Small dump cars carrying the materials are hauled up an external hoist to the hoppers on top of the 50-meter-high furnace. The charging of the furnace is kept under rigid control by automatic devices. This makes efficient management of the process possible. The furnace is charged in layers. Iron ore, coke, and limestone are introduced separately into the furnace at intervals of 10 to 25 minutes. As they sink down, they increase in temperature. The diameter of the furnace increases at the bottom. Where the diameter is widest, the temperature reaches 1600 degrees Celsius. The heat is generated by burning the coke. For the combustion process, hot air is blown through jets into the furnace via a ring of large pipes. This is the combustion area. The oxygen burns the coke, forming carbon dioxide. This chemical reaction provides the necessary temperature. Above it, the coke serves as a reducing agent. Carbon monoxide forms, which acts as the main reducing agent. The carbon monoxide combines with the iron oxide in the ore, forming metallic iron and carbon dioxide. As the ingredients continue downwards, liquid iron and slag is produced. The carbon partly dissolves into the pig iron. Hot gases rise and preheat the descending raw materials. Near the bottom of the furnace is a hole through which the liquid iron flows when the sealing plug is tapped. A modern furnace can produce about 11,000 tons of pig iron per day. Once in the air, the liquid iron oxidizes and a fine dust of iron oxide forms. This dust is sucked away by air and filtered. The slag, containing most of the impurities, floats on the molten iron. It is drained from another hole further up. It will be used as a building material. Any slag remaining is skimmed off before the iron reaches an insulated railway container and is transported to the nearby steelworks. Pig iron as a material is not very workable. It contains too much carbon, which makes it brittle and easy to break. Pig iron melts suddenly and crumbles away when heated, whereas steel keeps its shape. Glowing steel is workable and can be forged. It will bend rather than break, which means it's very tough. Pig iron has a very high carbon content. It also has silicon and sulfur, which makes it brittle. These impurities are removed through the Bessemer process. First, the pig iron is melted in the furnace. Before the Bessemer process was invented, the pig iron was puddled by hand to produce very small ingots of impure steel. They couldn't produce large items without joins. The molten pig iron is then poured into a pear-shaped Bessemer converter containing scrap metal. The scrap metal melts and mixes with the molten iron. Large converters reach a capacity of 400 tons. The actual process of steel production takes place behind closed doors. This allows the removal of gases and dusts by suction. After charging, the converter is turned upright. A water-cooled lance is lowered into it. Thousands of cubic meters of oxygen are blown into the charge with supersonic speed. The carbon within the iron oxidizes into carbon monoxide and heats the iron to white heat. This also oxidizes impurities such as phosphorus, manganese, and silicon. Their oxides are bound to the slag. Any iron oxide formed during this process is immediately reduced by special additives. All gases and dusts are blown out above the converter. After 20 minutes of oxygen blowing, the content of carbon is reduced to the desired level. Pig iron has been transformed into steel. A different process uses millions of tons of scrap metal in the production of steel. The electric furnace process makes it possible to recycle scrap metal according to its alloys, including stainless and highly alloyed steels. Scrap metal and slag-generating materials are poured into the already hot furnace. Impurities partially burn away during charging. Then, the heavy lid closes the furnace tightly. Graphite electrodes are lowered close to the surface of the charge. A high current flowing through the electrode arcs over the metal and heat is generated by resistance. Temperatures as high as 3,500 degrees Celsius melt the metal quickly. High-purity oxygen, coal dust, and dry lime are added in order to help remove any carbon or impurities still present. The furnace is tilted after 20 minutes, and the steel is poured into a fireproof vessel. Now the molten steel can be cast in a wide variety of shapes and passed over water-cooled metal rollers. A cutting torch separates them into equal lengths. The temperature is further lowered to transport them to the rolling mill. Here, the many different shapes, such as this slab, are heated in an oven to rolling temperature. In this case, the rectangular slab is to be shaped into a thin steel sheet. Fed through the first pair of metal rollers, the slab is squeezed to a few centimeters. For each successive pair of rollers, the gap between them lessens. The steel is becoming longer and thinner. A slab of 100 mm thickness can be reduced to 1 mm. In length, it can increase from 4 meters to almost 400 meters. When it reaches the end of the mill, the sheet is coiled automatically and cooled some more. The thick sheets can now be welded into pipes. The thinner sheets can be used in the manufacture of car bodies, containers, and many other products we use every day.